All right, welcome everybody. 5 p.m. Monday. Is everybody able to hear me? All right, perfect. Well, you're in your good luck crystal because I didn't plan for a quiz today, so all good. But remember, even if I give it today, it can only be about what we've done before. So if you stay on it, then you should always be and have all the tools to be able to do good. But for this time, nothing is going to be taking place today, which means most likely Wednesday. Yes, Henry, please stop by and pick up your test. I will send the solution tonight. So please, 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 make sure you email me, tell me when you're going to be able to come, pick up your test, compare it with the solution, redo all those problems, because they will come back. Yes, absolutely, absolutely. You'll have everything. The solution with the correct answer, and then your paperbacks. It's up to you to come and pick it up. Perfect. Any other questions? Okay, so last time we completed the NA series, the E series, we went over the pulleys. So we're now ready to go back and complete the Atwood one above. And once we finish with Atwood, then we will redo all those problems except the equilibrium ones, and we're going to add friction. Those are the S series. And then after that, we can do circular motion and drag, which will complete this chapter. So by Wednesday, we should be done, so that by next week, we can continue on energy. All right, so Atwood system. Atwood system are a great typical system, and you will have an Atwood system in about every test from now on. So make sure you master them. They will also come back in C270, and they will also come back in C271. Those are very typical problems, which are very, very interesting because they represent a lot of good techniques and good method that can be applied in any other situation. So those are good, typical type of problems. The big difference. Which part, Michael? The part with why Atwood is important, or what we have covered so far and what do we still have to cover in this chapter? Oh, this one, Atwood. Atwood is going to come in every test from now on until the end of the semester. So we're going to practice this type of problems using Newton, then using energy, and then we're going to revisit those problems as we include rotation, and redo it again using energy, and redo it again using Newton. Okay? So yeah, make sure you master all those problems so that you know, 3 points on the test. If you study them all, you know exactly how to solve them. Those are given points. Perfect. So we know how to handle the first law, the second law. We apply those laws directly on a system. We've seen cases where we have to use the third law. It's when we have more than one system. But what was specific about the type of problem that we use when we applied the third law is that the kinematics was exactly the same for both objects. The position, velocity, and linear acceleration were always the same for both of our systems that were connected to each other with the strain. Under such situation, we have the choice to pick object A or object B, or we could pick object A and B. And we could do this because the kinematics was the same for both systems. In the Atwood system, kinematics is different. And actually, that's not the problem I wanted to do. I'm sorry. Let's start with the first one. Hey, where do you go? Mouse, mouse, mouse. There, type 1. So it's a Atwood system where we have an object A and an object B attached together. We're going to pick 2 different masses, one bigger than the other, to ensure that the system is being accelerated. And we would like to figure out the acceleration of the system. we are only concerned about the magnitude of the acceleration. Since both object A and B are connected by a string that doesn't stretch, we know that the magnitude of the acceleration is the same. So if a problem asking us to get the acceleration of object A and another question of acceleration of object B, we know they're trying to trick us. Same thing, just do it once. But the big difference between this type of problem and the previous one that we've done when we applied Newton's third law, which was NA7 and NA8, is that the direction of those kinematic vectors are different. Let's say, imagine that we are going to consider MA, which is much bigger than MB. What is the direction of block A? Most likely, if you hang out 100 gram versus 1 gram for B. Is object A going to go up or down? Down, obviously. Perfect. Which means that object B is going to go up. So even though the string that connects them doesn't stretch, which means that the magnitude of the velocity and the magnitude of the displacement and the magnitude of the acceleration is the same for both systems, the direction is very, very different. Opposite, specifically. Which means that we cannot use Newton's law for both system A and B, because then on the right-hand side, we will have no idea what to put for the direction of the acceleration. Acceleration of A is down, acceleration of B is up. Therefore, they will have different signs. So an output system is a situation where the vector or the direction of the kinematic variables are different. If that's the case, we cannot take A and B as one system. We have to treat them differently and separately. So let's do that. We know from the given quantity that object A is going down and object B is going up. And they're both being accelerated. So, you have your notes in front of you. What was the choice that we agreed upon to do when your systems are being accelerated with respect to the choice of your coordinate system? If you know that the system is being accelerated in a particular direction, how does that help you choosing the coordinate system? Remind me what we said. Versus accelerated versus non-accelerated. Yeah, excellent. Let's pick one of the two axes in the direction of the acceleration. Excellent. So, right away, we're going to pick, say, X up, and we're going to pick X down for B and A, respectively. This will allow us, as we apply Newton's second law to both object A and B, since we're looking for the acceleration, that the AX component will be fully our vector, and it will be positive, and the Y component of the acceleration for B is going to be 0, which is nice because we have already 1, 0 in one of the two equations. And similarly, as we're going to apply Newton's second law to object A, the AX component will be the full A, and it will be positive, and AY again will be 0. So we managed to put 2 zeros in 2 of the force equations. Perfect. So let's pick a system and let's do Newton. Let's pick object B. What are forces acting on B? Let's go down to the list. First one that comes to mind is the weight. We have 2 different systems, so let's write them differently. MBG. And obviously, B is susceptible to a tension whose direction is up. And let's call it T. Easy peasy, 2 forces align along your X. Chapter 2 step will be a piece of cake. Let's do the same thing for A. Identify all the forces acting on A. First, the weight. This will be MAG. And obviously, it also is being susceptible to a tension. The tension is also going to go up. Do we know anything about this tension? Is there a particular law that we can use in order to relate this tension with a tension that we've already seen, say, in object B? Excellent. Yep. Thank you, thank you. By Newton's third law and the property of the pulley, we know those 2 tensions are the same. We need both property, right? Newton's third law tells us that this tension is the same as this tension, and that this tension is the same as this tension. And then the Poulies property tells us that this tension is the same as that tension. So we use Newton's third law here, then we use the property of the pulley here, and then we use third law again right here for us to be able to write down that this is also T. Make sure you write it down if you're in a WI section, because that's something that we want to see. Perfect. All right. So now let's apply Newton's second law to both A and B. How many equations are we going to be able to get for object B? How many scalar equations are we going to get as we apply the vector version of Newton's law into our coordinate system? Only one. Excellent, Kyle. Because all the forces are only within one axis. Good. So we have the left-hand side from the forces should be equal to MA, as we agreed. And this M, since we're doing object B, better be MBA. And I'm going to drop the subscript for AX. Good. And for AY, we have no forces on the left-hand side, no acceleration on the right-hand side. Done. Could you give me the remaining left-hand side? Could you give me the sum of the forces in the X direction for object B? What should go there as we apply vector analysis, as we project our vectors into our coordinate system? Excellent. T is positive. MVG is negative. Good. All right. So be careful. This G is a constant. It's 9.81. It's just a constant that shows up in the weight functional form. This is not the acceleration of your system. This is the acceleration of your system. And that's the one we're after. So obviously, we cannot get after A right now because we don't know what T is. So we have two unknown, but only one equation. When you get to that situation, no problem. You just pick another system. You know you're going to pick up more equations. If this new system is connected to the previous system, hopefully some forces will be common and will be disappearing. Those will be representing parametric variables. So let's do an apply Newton on A. Again, obviously, sum of the forces in the y direction will give us 0 is equal to 0. And in the x direction, blah, 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 will give us MA. A. Again, write down your math very, very carefully so that we don't do a sloppy job and call those two masses the same. Now, as we apply chapter 2, can anybody else give me the sum of the forces along the x direction for object A and be consistent with our coordinate system? So let's apply vector analysis basic rules. Could you add those two forces in the x direction and tell me what you have? Everybody should be typing. This is the easiest case ever, right? That's basic projection of vectors. Anybody knows the answer? Excellent. Perfect. One down, it's positive, and one up. So that's it. Only two force. No cosine, no sine. It's a piece of cake. The key is, this time, MAG is positive, and T is negative, because my positive x is down, same as the direction of motion. So that's a common mistake. People pick the wrong signs. Good. That's it. One more equation. A is the same. T is the same. Exactly, Jamie. Oh, yeah. Good. We understood with the uppercase, lowercase. That was good. Perfect. So, two equations to unknown. The rest is just math. You can solve for T. I don't know. Say from this, substitute it in the other. You end up with MGA plus MGB. Again, be careful. A and G are not the same. Let's substitute that here. And we got MAG minus, be careful of your algebra. Both terms picked up the negative sign. And now we can solve for A, the only unknown left. Easy. So, let's look at the functional form of what we just got. And does it make sense? Do we expect the acceleration to be positive or negative? Obviously positive, because we decided to pick our positive x in the same direction as the acceleration. Therefore, we knew it was positive when we wrote this. Therefore, this has to be positive. And this indeed is positive because ma is bigger than mb. So this is a positive number. Good. Obviously, you see that this is a unitless quantity. Difference of masses, sum of masses, you take the ratio, no units. And therefore, the units of A, meters per second, comes from the units of this stupid constant. You also realize that this represents the total mass of the system, or its total inertia. For an Atwood system, whenever you're going to be calculating the acceleration, the bottom will always have the total inertia. Keep that in mind. If you see a negative sign in there, you know something went wrong. So you can always make sense of each of those terms. ma better be positive, because ma is the one that provides a positive acceleration. And then the bigger mb will be, the less the magnitude of A will be. So it goes against it. That's why we have a negative sign. Okay? Question on a basic Atwood system. All right, let's do another one. Let's do type 2. Same question. This time, instead of having B hanging in the air, we're going to put B on a horizontal table. Same thing. We're going to pick two masses, MA and MB. And for this one, we don't have any limitation of their respective masses. As soon as we're going to put the non-zero mass on A, guaranteed, we're going to have an acceleration. Okay? So, obviously we have a composite system, and we're being asked to figure out the acceleration of our system, either A or B or both. Therefore, we know we're going to use Newton's second law. Since object A and object B are connected, we know right away we also are going to use Newton's third law and the property of the pulley as we're going to compare the two systems. Since we also can confirm with 100% certainty that object A is coming down and object B is being accelerated towards the right, we know right away that the current system for A will be like this, and the one for B will be like that. So that one of the two axes goes in the same direction as the linear acceleration. Perfect. All right, let's do a free body diagram somewhere. Let's apply Newton's law. Let's apply it on object A. Seems to be easy enough. Should be similar to the previous problem. As we identify system A to be our system, the external force acting on object A must be first the weight, second the tension. Nothing different from what we've just done. Perfect. All those forces are aligned within either the x or the y, therefore all the directions are taken care of, therefore it is a complete free body diagram. Easy. Let's do the one for B. Similarly, we have the weight, mbg, we have the normal force, and we have the tension. At this stage, we realize that this tension, because of Newton's third law, is the same as this tension going left. As we apply the property of the pulley, this tension is the same as this tension coming down. And as we apply Newton's third law again, this tension coming down is the same as this tension coming up. Therefore, those two buggers are the same. Perfect. Again, all those forces are aligned along either x or y, so the chapter 2 part will be trivial. Let's write down our equation. In the x direction, we are going to get the same as before, mag minus t is equal to maa. And in the y direction, we have no acceleration, and in this case, we have no forces. Easy. Object B. Some of the forces in the x, some of the forces in the y. In the x, the only one that survived is the tension. Therefore, the tension must be equal to MA. And we're doing object B. Therefore, this is MB. All right, I don't know why. We have two forces, N minus MBG. And the sum is equal to 0. There is no acceleration physically in our chosen y direction. Good. So we have 4 equations. This one is useless. This one won't be needed. But I wrote it down because we will need it very soon as we introduce friction. Therefore, for our case, if we're looking for the acceleration, we only have to combine those 2 equations. As you're going to do so, you're going to end up with a very, very similar functional form. MA is the one that will cause an acceleration. The bigger the MA, the bigger the acceleration, positive. Gives you need less quantity. And at the bottom is always the total inertia. Inertia of A plus inertia of B. Mass of A plus mass of B. Something. Oops, and this should be a square. Okay? So technically, type 2 is even easier than type A. Questions on type 2? No questions? Everything is good? Alright, alright. Okay. Let's do another one. Type 3. And don't worry, I always lose track of type 1, 2, 3, 4. Don't worry. Type 3. Okay. Again, same thing under the trees. Except now the table is not horizontal. Okay. Let me slow down. But the table is inclined by 30 degrees. So it's, I don't know, it's a weird table. So let's do the same thing. Let's imagine MB is given, MA is given. Let's call this alpha given, and that's it. Let's figure out the acceleration. In this case, we are not able to figure out the direction of motion. It's a 50-50. B could go down, and if B goes down, A goes up. Or B could go up, and if B goes up, then A goes down the inclined plane. How are we going to know that? Well, we need to know the respective magnitude of the masses. If mass is much bigger than the mass of B is much bigger than the mass of A, obviously B is going to go down, and A is going to go up left inclined plane. So, if the masses are very clear, and it's obviously one is much bigger than the other, then you can guess direction. If the numbers are very close to one another, you may not be able to guess. You will always have an uncertainty of a factor of 2. You will know the direction of each, but at least the line of the direction. But you can always go forward or backward. That means sometimes you are going to have to guess the direction of one of the vectors that you're dealing with, which is the acceleration. Keep that in mind. Every time you're going to guess the direction of a quantity, if after you solve for its magnitude you end up with a positive value, you guess correctly. But if after your algebra and at the end of the problem you end up with a negative value, then remember what we said many times before, the negative sign will reflect an opposite direction. Therefore, you will know that you assumed the wrong one. That's okay. Just state it at the end, you don't have to redo the whole problem. But make sure that you take notes and you point it out. I will take out points if you ignore negative signs, because they will mean something. So, what do you want to do? Do you want to assume that B goes up and A goes down, or would you like to do A up and B down? B down. Alright. So, if B goes down, then obviously I'm going to pick my positive X down. The Y, don't care. And if B goes down, then A is going to go up the inclined plane, so I'm going to pick my X along my inclined plane. And Y perpendicular to my inclined plane. Okay? As I'm going to use Newton's second law. Jamia, so yep, exactly. Same as forces, absolutely. If the magnitude of your acceleration will end up being positive, then you guessed its direction correctly. If you end up with a negative sign, you just guessed it incorrectly. No biggie. And you will only know this, Henry, if you're given the value of MA and MB. Numerical value, yep. Perfect. All right. So we've picked one dimension or one direction. Make sure you redo the exact same problem at home after the collaborate session today, and assume that it goes in the other direction. Redo the exact same problem with a different assumption and see the difference in your functional form. Correct. Let's apply, we're looking for the acceleration. We know B is being accelerated. Let's just take B as one of our systems. If B is our system, the external force acting on B are exactly the same as the last two problems. You're going to have the weight, MBG, and the tension. Both happens to be aligned with our x-axis. That is nice and easy. Done. Complete free body diagram. Now let's go to A. Again, first external force that comes to mind is the weight, straight down, and this is MAG. Then A is obviously subjected to a normal force because it lies on an inclined plane. But we've done all those any problem with inclined plane, so we can handle that easily. We know right away that there is normal force. Let's call it NA. And obviously, A is being susceptible to the tension, to the strain. And this is where we realize, as we write this label, that because of Newton's third law, this force is the same as this force coming down. Because of Newton, the property of the pulley, this force coming down is the same as that force coming down towards B. And now, again, by using Newton's third law, if there is a force coming down, then it is the same as the force coming up acting on B, which is the one we call T. Hence, this is T. Okay, so there is 3 steps in identifying the relationship between those two tensions. And we applied the Newton's third law twice. I'm always stressing that out and going step by step because first of all, if you're WY, you're going to have to write it down. But worse, we're going to lose the assumption as we start rotation. So we cannot just take it for granted. Assume it and then forget the assumption that was made. All right, so 3 forces. Let's complete our free body diagram. Obviously, this is not complete. T is aligned X, no problem. NA is aligned Y, no problem. But the weight is not. Therefore, for us to be able to express the weight in component notation and be able to add them up as we apply Newton's second law, we need to figure out the direction of this weight. Obviously, the weight has something to do with alpha, because that's the angle of inclination. So the question is, where is alpha? Is it towards the right, or is it on the left? Michael suggests it's on the right, and we confirm this using the 2-step process. All right. This force that we're interested in is perpendicular to this line that creates your angle. So let's forget about it, and let's focus about this line. And obviously, this line is perpendicular to our y-axis. Therefore, alpha is between our force and the y-axis. Perfect. Now we're ready to apply Newton's second law. This one, easy peasy, same as before. MBG minus T is equal to MBA. Same as before, third time. Again, we're looking for A, but T is in the way. So we need one more equation. Let's apply Newton's law on object A. Both direction, first X, second Y. The X component of T is T. The X component of NA is 0. And the X component of the weight is negative MAG sin alpha. That's where all that vector calculus projection comes in. And now we plug the physics. This is object A. Therefore, this must be MA times the acceleration. And it's the full vector, the full acceleration because of the choice of our coordinate system. We know that A is along the X and 0 along the Y, which means right away, boop, 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 bing. And in the Y, just for good luck and good karma, NA minus MAG cosine alpha, which again we will not use in this particular problem, but we will later on as we introduce friction. So really, we have a system of 2 by 2. Easy. Again, addition, substitution. Here we might want to try, we did the substitution earlier. Let's try the addition method. Let's try to add equation 1 with equation 2. If you do this, T will disappear, which is what we want, because we only care about A. So if you add those two equations, you end up with MPG minus MEG sin alpha is equal to MDA plus MAA. Hence, as you saw for A, you have MB minus MA sin alpha divided by, again, the total inertia times G. And again, you notice very, very similar functional form. We have assumed that B was going down, which implies that MB is bigger than MA. Sure enough, MB is the positive term. MA is the one that has the negative term. The mass of A is going to influence the acceleration opposite to the mass of B. So A is against the acceleration. The bigger the A, the less will be, the bigger MA, the less will be A. Sure enough, he has a negative sign. Again, total inertia, plus, 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 plus in the bottom, and then a unitless quantity. And then our favorite G. So please redo this problem again. Assume that MA is bigger than ME. Assume a different direction of motion for block A and B, and see how your final equation will be different. What you will end up with is the exact same functional form, except with a negative sign, which will be confirmed because if you assume that B goes up and A goes down, obviously MA will be bigger than MB times the sign. All right? Any questions so far? Alan asked, is A the same for both blocks? Yes. Remember, that's how we started the problem. The magnitude of A is the same for both blocks because the string doesn't stretch between the two blocks. But obviously, the direction is different. And that's the reason why we cannot consider A and B as one system, like we did in NA7 or NA8. So the velocity should be the same, the acceleration should be the same, the displacement should be the same in magnitude. But all the direction of those kinematic variables will be different for both systems. You know, I add those two equations. I use the addition method. I added equation 1 with equation 2, which allowed the T to disappear. I just wanted to go over both methods. Some people like the substitution better, some people like the addition better, somebody may combine the two, whatever you like to do, I don't care. Just make sure you do it fast and make sure you do it right. And make sure you can do it in literally 30 seconds, whether you're dealing with a 2 by 2 or a 3 by 3 or a 4 by 4 or 5 by 5. Make sure you learn yourself how to teach, you teach yourself how to use your calculator and use it efficiently. Then you can focus on setting up your problem and focus on the physics or the engineering so that the math is not on your way. All right. Any other questions? As you may guess, all we have to do to increase the complexity of an actual system is just to add another inclined plane. That's it. And if you look at your book, you will see other output systems. So do them all. Do them all from the website, all from the book. Because you know, one is going to show up at least once, most likely two. I would ask you to solve it using Newton, and I will ask you to maybe solve the exact same problem or something similar using energy. That's going to be the next two chapters. Same question. we know MA, we know MB, we know alpha, we know beta. Let's assume we do not know the direction of motion just yet, because they tell us that they give us MA and MB, but they never gave us the numerical value just yet, or we just don't care. So let's pick a direction of motion. Let's imagine that the direction of motion goes in this direction, which means that B is going down and A is going up. Okay? Again, we could pick the other, doesn't matter. This dictates our coordinate system. We know right away that we're going to choose a coordinate system such that positive x is in the direction of motion for B, and positive x is in the direction of motion for A. So we know right away that center forces in the y direction will give us 0 for both objects, and that the MA term for both systems in the x direction will both be positive. So we can never take the risk of forgetting to add the negative sign. Alright. We're looking for the acceleration. This involves, obviously, that we're going to use Newton's second law. All we have to do is figure out the left-hand side, which is the sum of the forces, and then we can deduce the right-hand side. And we notice that we have more than one system, therefore we know right away we're going to apply Newton's second law on object A and object B. Then we're going to use Newton's third law to connect those two systems twice. And then we're going to use the property of the pulley, which is the property that we're going to lose on chapter whatever, rotation. Alright. Let's do a flexibility diagram on B. Let's see what that leads. First force that comes to mind, MBG. Second that comes to mind is the normal force. Normal force is perpendicular to the surface on which our system is located, and it acts on our system. Therefore, N must be going towards the positive one. Similarly, object B will feel a tension, trying to pull him back. That tension is going into up, same direction as up the inclined plane. Therefore, along the x, opposite direction. Good. Alright, let's look at our coordinate system. Is there anything that we still need to do to complete it? Absolutely. We need to figure out the angle for the weight. So, is object B going to, or the weight of object B going to be dependent on the angle alpha or the angle beta? Beta, of course. Perfect. And so the next question is, where is beta? Is beta between the weight and the y-axis, or is beta between the weight and the x-axis? Carl suggests x. Are we all good? Ah, no. Change his mind. All right. It is indeed between y and x and mg. Perfect. Good. Good use of method, because getting it. Good, good, good. That's it. We're good to go. Now we can just do the math. Let's complete a free diagram for object A. Again, we're going to be facing the weight strictly vertically down, pointing down. The normal force perpendicular to the surface on which is lying on. Let's call this NA, so we don't mix it up with the other N. So let me change that label to NB, so there's no ambiguity. And then again, we notice that there's a tension here. This tension is the same as this tension by Newton's third law. Then by property of the pulley, this is the same as this tension by the property of the pulley. And again, by Newton's third law, this is the same as this force. Hence, this is T. All right. Let's look at those three forces and the relationship between T, NA, and MAG with respect to X and Y. Obviously, T is taken care of, NA is taken care of. We just have to worry about MAG. Obviously, MAG has to do with alpha. So where is alpha? Between MAG and the x-axis, or MAG and the y-axis? Y again. Excellent. Done. Alright, now let's use Newton. Vector. That's the easy part. That's why we mastered chapter 2. So now life is easy. This is trivial, negative t plus mvg sine. And this is equal to, I'm doing object B, therefore this is MBA. Good. And then for good karma, MB minus MBG cosine. And that's equal to 0. Again, that's due to the choice of our coordinate system. So far, so good? Alright, let's do the same thing with A. This time t is positive and the weight is negative. And the weight will be MAG sine. And this is alpha. And this is MAA because I'm applying this to object A. Similarly, this will be 0, and for good karma, we're going to have NA minus MAG cosine alpha. And as you look at the equation again, you realize, oh, I don't need the equation 2 and 4. I just need the first one and the third one. And sure enough, as you're going to combine this, we can use the addition method again, because there is a t in one and a negative t in the other. We're going to have MBG sine beta minus MAG sine alpha. That's equal to MAA plus MBA. Hence, A is equal to MB sine beta minus MA sine alpha divided by the total inertia again times G. And again, the sign should make sense. If we assume this direction, then somehow the component of the weight along the x direction is going to be bigger than the component of the weight of A. Sure enough, the mass term for B is the one that has the positive sign, that's the one that contributes to the assumed direction of the acceleration. And MA is the one that's going to try to slow it down, hence the negative sign. And as you can see, because of those beta and alpha, sometimes it's not very clear from the beginning which one is going to win. Hence, we have to assume something. And as we mentioned already 3 times, if this ends up being positive, then we made the wrong assumption, the right assumption. We can just leave it as it is. If you end up with a negative sign, as you plug numbers, make sure you don't ignore it. If you end up with A is equal to negative 1.2 meters per second squared, you have to address this. Just tell me. Wrong direction for A. Oops, no worries. Don't freak out. Michael, just to double check, why is the t in B negative and the excellent. Coordinate system. Look at your positive x. Look at your t. Look at your positive x. Look at your t. Excellent. Remember, from free body diagram to equation, it's strictly back to vector again. Calculus. Calculus 3. Okay, so all chapter 2. Chapter 2, chapter 2, chapter 2, chapter 2 is going to haunt you for the rest of the semester. Chapter 2. Yep, we mentioned it twice. Right? We mentioned it here, and we mentioned it there. Absolutely. No. Like I said, Jimmy, if you end up with a negative sign, just justify it. Wrong direction for the acceleration. No problem. As long as you know what it means. That's all I care. Because you're going to need you're going to use not ignoring it later on as we combine free body diagram. It's going to become very, very important. Especially when you are going to study trusses and bridges. If you ignore them, you're always going to get it wrong. If you don't, you're always going to get it right. Exactly. Since you know that those are scalar equations, which means that all those variables represent the length of those quantities. If that quantity is a vector, since they're being represented by their magnitude, they have to be positive. Because the length of vector, the magnitude of vector is the length. Always positive. The sign is always given to you with respect to their direction. Right? If my velocity is here, and it has 4 units, the magnitude is 4. But in this case, if I decide to pick this coordinate system, then V is positive 4. But if you decide to pick this coordinate system, then your V is negative 4. Okay? So now look at the other way around. If now your coordinate system is set, but now you don't know whether the V is, say, in this direction or that direction. Is it V1 or is it V2 or is it A1 or is it A2? And you have to guess, well, what is the relationship between 1 and 2? Negative, by property of a vector. So that's why any negative sign that you end up after your system equation must come from the wrong choice of the direction of your vector. Whether it's displacement, velocity, acceleration, or forces, always the same. So you know exactly how to fix it. Okay? Good. Any other questions? Perfect. All right. Atwood, again, please master it. If I grade tests and I get to the Atwood question and it is not a perfect solution, then I know that that person either don't care or never spend the time, because I'm going to repeat this over and over and over. But if, as I grade, the solution is perfect, then I know that that person has been studying. Perfect. So, last, friction, and then circular motion and drag. Let's put friction there. What have you learned from friction? Friction can be represented graphically very easily like this. Hop, hop, hop. Done. That's all there is to know. All we have to do now is put some label and make sense of that graph. This is friction on your dependent variable. Independent variable will be the net force in the direction of F, parallel to the direction of F. Very important. So this is the sum of a bunch of vectors in a particular direction that happens to be the direction of the friction force. So what we're going to be doing is, since we know that friction is a surface friction, obviously the direction of friction will always be in the same direction as the motion. But again, it can be a 50-50. So this means that this will be the sum of the forces along the x direction, usually, if we pick positive x to be in the direction of motion. Two parts, left and right. Let's use caca color. Sorry, let me change that. Okay, left side, no motion. Here, motion. You will make a note, and very important note, that I didn't use accelerated or non-accelerated. Okay? If there is no motion, this is the first law. It has to be the first law. But if there is motion, it still can be the first law here. It all depends on what kind of motion. So Newton's first law can only be applied on the left side, but Newton's first law can also be applied on the right side if the velocity is constant. If the velocity increases or keep changing and decreases, then we know we can also apply the second law on the right hand side. Okay, so the limit doesn't separate the first law from the second law. No, it only separates the motion from the no motion. Perfect. Left side is where Fs will be. The right side is where Fk will be. There's going to be two types of friction. Static friction, Fs, kinetic friction, Fk. Hence, whenever there is no motion, Fs is present. When there is no relative motion between your system and the surface, or any contact, Fs is the one that pops up. As soon as we start moving, Fs will disappear and let Fk take over. Weird thing. Nature is watching us. Again, same as the normal force, or third law. Now let's look at the functional form of Fk. It's obviously a straight line, same as Fs, but what's the difference between this straight line and this straight line? If they both represent static friction and kinetic friction. What's interesting here? What's the difference between those two lines? You know the property of a line? What's different between the two? There's two things. The one is more important than the other. Yeah, slope is different. Excellent. Which implies, thank you, Henry, that if the slope is 0, obviously the value of Fk is constant. And obviously, since the slope is not 0, thank you, Michael, the value of Fs changes. Let's remember that. The value of Fk is always the same, constant. Doesn't matter whether you're moving at constant velocity or being accelerated. However, if you're in a static situation, Fs can take all possible value. Alright, if this is a constant, 0 slope, then obviously its value must be a constant. Sure enough, its value is equal to the coefficient of kinetic friction, Uk, times our usual normal force. Look, it's not max. This is max. This is below the max, right? We have all those possible values for Fs. But we're getting there, Kyle. But does that make sense? This value is constant, but this value is less than those values. So Fk can be either bigger than Fs if Fs is here, or it can be less. Both situations. Alright, but what's important is it's constant. What's also important is the introduction of this term. This is equal to this. This is a force. This is a force. Therefore, this cannot be a force. It's a coefficient. It has no units. Therefore, we can use the equal sign. Do not mix up the coefficient of kinetic friction with the force of kinetic friction. Two different things. Okay? Please make sure you take notes of this. People always mix them up. The value of mu k will give us information about the strength of Fk, obviously. Because N is a constant force, the bigger mu k is, the bigger F will be. So mu k is a positive number, doesn't have to be an integer, can be a floating number, from 0, strictly bigger than 0. And most of the time it's less than 1, but it can go a little higher. Alright, so Fk, we know its definition, like the weight. So on the list of forces, we had the weight, normal force, any pulling, pushing, and the last one is friction. Therefore, if you're dealing with a case where the object is moving, then you know right away that you will be using Fk as your fifth type of force. Fourth type of force. And not only you know its magnitude, mu kn, and you know you can get n from solving your system equation, so perfect. But you also know something about its direction. If you're sliding on the ground and there's friction between you and the ground and you're going forward, how will your leg feel? That is, what do you think the direction of the frictional force will be? It will be in the same direction as your motion, sliding motion, or will it be opposite? Excellent, opposite. Perfect. That's how we define Fk. Fk has a magnitude of mu k times n, constant. And its direction is opposite to the direction of motion. That's how we define Fk. Make sure you write that down in your notes. We're getting there, Crystal. Excellent question. For Fs, we're going to have some problems, major problems, because nothing moves. So when it moves, it's very clear. We usually always know what is the direction of motion. And therefore we can deduce, oh, okay, if I know that this system is moving in this direction, whether constant velocity or accelerated, we don't care. We can identify that direction, then we know right away as we apply Newton's method and we identify the external forces acting on the system, we're going to pick the direction for Fk, which is opposite to the known direction of motion of our system. And we memorize its magnitude, therefore Fk is usually the easiest one to identify and work with, because we know both its magnitude and its direction. The problem is Fs. Fs shows up when the system doesn't move. So the first thing we don't know is the magnitude. Obviously, the magnitude goes from 0 to a maximum value. It can take all possible values. So we don't have a formula for Fs the same way as we have for Fk. We're going to get Fs by just writing it Fs. We will not assume anything about its magnitude, and then we're going to add it into our free body diagram. That's all we can do. And solving for this equation of Newton will give us the magnitude of Fs, the same way as solving for Newton's equation gives us the magnitude for the normal force. So we're just going to treat it as any other force. So in that sense, it's actually easier. But then the problem arises, as we're going to include that force in our free body diagram, we know that it is also a surface friction. Therefore, that Fs should be along the same line as the direction of motion. But if our object doesn't move, where is going to be Fs direction? We're still facing a 50-50. And we don't know. So we have to rephrase the direction of the definition of the direction of Fs by Fs direction is opposite to the tendency of motion. Big difference. Because obviously, if it doesn't move, then we cannot use that. So it's the tendency. And the tendency of motion is given to you by this factor. That is, if you pick, you know that the possible direction of the direction of motion possible is here. Obviously, you're going to pick one of the axes along that direction. If the object moves towards the right, obviously you know that Fk is present, and you can write it as a force that goes towards the left. And you know its magnitude. No problem. If not, the system is at rest. This object is not moving. The only two directions it may move towards is up the ramp or down the ramp. So you know that static friction is either up or either down. It will depend on the magnitude of other forces. We have no idea. So we need to know the tendency of motion. That means we need to identify all the other forces. 1, 2, 3, 4, and calculate the sum of those forces along the x, along the possible tendency of motion. If the sum of those forces is positive, then we know that the tendency is to go up the ramp in my positive x-axis. Therefore, Fs will go down. But if, as I calculate the net force, I end up with a negative number, then obviously the tendency of this system is to go down, because it's negative opposite to my x. Therefore, we know it's going down. Therefore, as I'm going to choose Fs, I'm going to choose it up. So Fs is much more complex than the Fk, because we don't know its direction, 50-50. So either you use this to figure it out, or again, you can guess. And as we said earlier, if your value for Fs is positive, you guess the right direction. If it's negative, you know you guess wrong. Okay? So we only know the direction of Fs. And the only way we can figure out the direction is to do this test. Otherwise we can't. And we know nothing about its magnitude. It can be 0, or it can be any value in between until a specific value right here. Let's look at this point. What do you notice? You notice that the static friction increases linearly, then suddenly it's going to drop. This drop occurs between a no motion state and a motion state. Is that something we can relate to or not? That is, if you're trying to move a major desk, super heavy, so you apply a force here, F. Obviously, the possible direction of motion is here. So I'm going to pick my coordinate stem like this. Exactly, Tyson. You're right on it. If I apply a force F, which is 0, then obviously the tendency of motion is towards the left. Therefore, you know the direction of Fs is towards the right. But if this force is 0, then Fs is 0. So I'm right here. Let's say I increase F to 2 Newton. Obviously, if this is the only force along my chosen x direction, and now it becomes 2 Newton, then the floor is going to know about this, and is going to create a static friction, which is opposite to the tendency of motion, therefore towards the right, and its magnitude will match exactly the 2 Newton that I applied to. Therefore, we know this is a 45-degree angle. So as you're going to increase the net force, in this case I only have one, in the possible direction of motion, Fs will just match it every time. Until this force big F is big enough that the system is going to get moved, as Tyson suggested. And you've all experienced this, I'm sure. You try to move a big table, you push. So the friction is getting bigger and bigger and bigger. But as soon as you get it to move, for some reason, you don't need to apply the same force. It seems easier. You can apply a less force. That's the drop. The force that you need to apply that matches the maximum force, friction force, then this is going to drop as soon as you start moving. So that's the reason why it's always easier to get an object to move than to keep its motion going if you deal with friction. Okay? What we're interested in is to which maximum value can the static friction take to counteract the net force. It has one, and this one will refer to Fs max and Fs max only. And this is defined as mu Sn. Be very careful, those look very, very similar. And yet, they are very different. This is mu s, coefficient of static friction. This is mu k. This is obviously a constant for all cases when the object is moving. This is only true if you know that Fs takes its max value. That's maybe 1% of the cases that you're going to be dealing with. 99% of the cases, you're going to be here. Therefore, you cannot use this. You have to know for sure that based on the physical constraints, your net force is such a value that Fs becomes maximum. Fs max. This is the maximum value for Fs. Only here. This is Fs, all possible value. This is the maximum value you can take, Fs max. Only if you know that you're here, or that the situation is such that this value for net force happens to match this value for F, only then can you use this. Otherwise, you cannot use that. So, how are we going to know whether we're here or not? Just look at the keyword, 3 keyword: min, max, about to move. If you see any of those 3 keywords, make sure you add it on your method. You know for sure that Fs is taking a maximum value, then you can use this. If you don't see any of those 3 keywords, you cannot use mu Sn. Make sure you write that down, please. This is where most people make mistakes. They forget their definition. Make yourself a little cheat sheet with the method that we use. By now, you should have 4 or 5 different cheat sheets. One page with Newton's method, another page with the list of forces, and then another page that confirm which coordinate system you pick, whether you pick accelerator or not. What else did we see? That's pretty much another cheat sheet to figure out the angle between your force and either your X or the Y, a two-step process. Now include this in your additional cheat sheet. Okay, and keep them as you do problems. Michael asks, is there a way to tell if you're, yes, like I just said, the only way to tell. Oh, yeah, I was getting there. Thank you. The only way to tell whether you can use μSN, which means that Fs has taken its maximum value, is if you can find any of those three keywords: minimum, maximum, or about to move. About to move makes sense because that's where we cross the limits. Max makes sense because max can refer to Fs. Min doesn't make sense, but min doesn't have to refer to Fs. Min could refer to another quantity in the problem. Doesn't matter. As soon as you see any of those three keywords, min, max, or about to move, you know that if you're dealing with a system that doesn't move, you can use μSN. If you do not see any of those three keywords and the system is not moving, you cannot use μSN. And you don't know its direction either. Those are going to be the hardest cases. But again, as I mentioned earlier, you can just guess. You'll get away with it in this class. Nope. Remember, Fk is not the same as μk. Fs is not the same as μs. Fk equals to μk times the normal force. Fs, if it is maximum, equal to μs times the normal force. So F and mu are not the same. I repeat, write it down. I already mentioned it an hour ago. You should have taken notes. The force and the coefficient are not the same. Make sure you write this down so you don't forget. The coefficient is just a number. The force is a force. They cannot be the same, because if they were the same, they would have units of Newton, and this also have units of Newton. So we have units of Newton squared on the left-hand side, and to the power of 1 on the right-hand side. Cannot be right. This is just a stupid number with no units. Fs is associated with Fs maximum only, and μk is always associated with Fk, but they are not the same. Is that okay, Kyle? That is very important. Excellent. Thank you. So please write that down, write that down, write that down. Seems like we get lots of questions during Collaborate that are based on something that I've asked you to write down the day before or the week before. Please take notes. You can't survive science if you don't take notes. Otherwise, welcome to class. You can just pick up a book. Okay? Usually coming to class is useful because the faculty, or whoever's teaching it, in general, not always, is trying to focus on the essential. So you want to get as much as possible from those sessions. Many of those tricks or method never shows up in books. Books usually are more like reference books. Okay? Question. It depends. 90% of the time, μs and μk will be given to you, Michael, unless that's the question. Unless the question is asking you, okay, calculate μk. And obviously, you know, okay, my system obviously is moving. But usually, if the question is not asking for you to calculate μs or μk, I will always give you both. So, for example, let me change screen. If I give you another object on the inclined plane, at rest, therefore it's at equilibrium, and I'm asking the same question as before. Figure out the normal force. And say, I don't know, figure out the weight. If I give you, oh no, not the weight, the normal force. If I give you the mass of the object and you see μs and μk given to you, those are the keywords. 0.5 and 0.2. This is the hint for you. You have to include friction. But I will always give you both, Michael. Because you have to be the one to decide which one you're going to use. Sometimes you will be able to use mu k if you're moving. Sometimes you're going to be able to use mu s if you're not moving and fs is max. Or sometimes you won't be able to use any of the two. That's for the case where you're right here. You're at rest and fs doesn't take its maximum value, which means that you've never seen any of those three keywords, ever. Does that make sense? Excellent. Kyle, I was just curious as to where... Oh, okay. Good question. They're nowhere to be found. They do not have a geometrical interpretation. The coefficient. Because coefficients are always multiplied by the normal force in both cases. Good question. Good. All right. Oh, I'm sorry, I went over. Let's take a break. Let's take a quick break and let's apply all this to our problems. So, revisit your notes that you've taken when we went over the description of this diagram. Take notes in your own words so it makes total sense to you. And then, by the time we come back from the break at 6:22, your notes will be written and completed and specific to your liking. We're going to be able to address them and apply all those stupid rules and methods to the similar problems as we did before, but let's include friction. All right, let me turn off that little... Okay, so let's apply friction to those problems. But before we do so, is there any additional question concerning friction? All right, so let's start with F2. Mu s only at Fs max. Correct. Mu s, the coefficient of static friction mu s, can only be used in the definition of Fs if we know that Fs takes its maximum value, which is also known if and only if we see any of the keywords minimum, maximum, about to move. But Fs does not depend on us in general if you don't see those keywords. Good. Good. F2. All right. Same question. We're given the mass. We're given the angle alpha. We're given us and uk. Therefore, we know there is friction on the inclined plane. We're given F, and we're being asked for the normal force and friction. All right. We only have one system. Oh wait, we need to know what's going on. It's maintained at equilibrium. Okay, so it doesn't move. If it's maintained at equilibrium on inclined plane, then the system doesn't move. So, if the system does not move, are we going to be dealing with Fs or Fk? So, write down those questions and add it to your method. When you know that there is friction in the problem, the first thing you ask yourself is, what kind of friction am I dealing with? Excellent. It's got to be Fs, because we're not moving. It's maintained at equilibrium. Good. So, guarantee it's Fs. Okay, so the first question you need to ask yourself is my system moving or not? If it's moving, you know you can use Fk. If it's not moving, then you know you have to use Fs. The problem is, as we answer yes for Fs, now we need to ask ourselves a second question, which is Fs taking its maximum value in this problem or not? What is the answer? And how did you figure it out? How are you going to know whether Fs is max or not? As you read the problem carefully. F2. Mabel suggests we're going to be able to use μSN, which implies that Fs takes its maximum value. How do you know that? The fact that it's maintained in equilibrium allowed us to decide that Fs needs to be considered. That's not enough to answer the question, is Fs max? Let's go back to the previous board. If we are in motion, we use Fk. If we're not in motion, we use Fs. Next question, is Fs here, 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 or is Fs max? How do we answer, how do we know if Fs is max? Excellent. We have not seen any of those three keywords in the problem. Therefore, we are somewhere here. We cannot use μSN. Does that make sense to everybody? Two-step method to figure out which friction you're going to be dealing with. Don't skip those two questions, because the main source of error is people pick the wrong frictional force, always, and then they pick the wrong direction. Okay? Two-step process, like figuring out the angle of those stupid weight or normal force as you do a free diagram. Two-step. Here again, two-step. First question, is my system moving or not? If it's moving, you know it's Fk. Fk is the easy case. You know its magnitude and its direction. If it's not moving, you know it's Fs. But now the next question you ask yourself is Fs taking its maximum value or not? And for you to answer this, look for keywords. If you see the keyword min, max, or about to move associated with anything, you know Fs takes its maximum value. Therefore, you can use μSN at least. But you still don't know its direction. All right. So, therefore, we know there is friction, but we know we cannot use any of those values. Are we clear on this? Since we're at equilibrium, we don't move, and we know that Fs is not max, we cannot use μs, we cannot use pk. All right. So, let's apply Newton's law. Let's figure out the normal force and the friction, which we know now is static in this particular case. This obviously is our system. Let's go through the method and the list of forces. First, the weight will show up, as usual. Second, what force comes to mind? Excellent, normal force. Perpendicular to the surface, applied on our system. Any pulling, pushing? Yeah, that's stupid F. Horizontal. And last one, we know there is friction. It's a surface friction. Therefore, friction has to take place along the inclined plane. Friction has to be along that dotted line. What we don't know is Fs pointing down or Fs pointing up? So we don't know its magnitude, that's what we're looking for. And worse, we don't even know its direction. But remember, we can get this direction using two different methods. First method, you guess. And in this class, you will get away with it. You're just going to pick up the negative sign, and you just know, okay, well, I picked the wrong one. Let's move on. It may not work in Situ 71. Hence, the other method that will work all the time is to identify the net force along the possible direction of motion. Therefore, we need to identify the net force along this direction. Question, is the opposite to the tendency of motion? Yeah, it's the opposite to the tendency of motion. Therefore, we need to figure out what is the tendency of motion. The tendency of motion is obtained by doing this calculation. So if we do this calculation, if it's positive, we know it's opposite. If it's negative, we know it's opposite. But we need to figure out what is positive, what is negative. That's where we pick a coordinate system. So in this case, you definitely want to pick a coordinate system such that one of your x-axes is in the possible direction of motion, either the x or the y. And the net force has to be along the x. because x is the direction along the possible direction of motion. So if you look at your forces, obviously there's two forces that have x component, F and mg. N doesn't. So this will involve only two guys, Fx and mgx. So we need to figure that out. Let's complete our free body diagram. We need the direction for both, the weight and F, in terms of alpha. Where is alpha? For the force F. Is alpha between F and X, or is alpha between F and Y? F and X, excellent. Similarly, is alpha between the weight and Y, or is it between the weight and X? I got conflicting answers. All right. Thank you. Perfect. Okay. So now really all we have to do is do this test. This is Fx plus mgx, right? This is Fx. This is mgx. We're expert in vector notation now. What is Fx? Can you give me its functional form? That's obviously the adjacent of a right-angled triangle. So Fx is what? In the x direction. Chapter 2. What is this? It's taking too long. You have to revisit your vector. This should come in 2 seconds. Basic decomposition of F along your x. Is this the adjacent or the opposite? Adjacent. Excellent. Thank you, Gibson. Therefore, it's going to be cosine. And it's going in the same direction as your positive x. Therefore, positive. Positive F cosine alpha. What about the x component of the weight? It's obviously going opposite direction. So this one will have a negative sign for sure. What is it going to be? Sine or cosine? Is this one the opposite to the angle or adjacent to the angle? Opposite, therefore sine. Excellent. Calculate this. If this is positive, then obviously the net force is going in your positive direction. Hence, Fs will be down. If this F cosine alpha minus mg sine alpha is negative, then it means that the net force along the inclined plane is going opposite to your x, is going that way. Therefore, friction is going up. Okay, so it all depends on if the component of the weight along the inclined plane is bigger than the component of F along the inclined plane. So you just add all the forces that have an x component. Do this test. If you assume positive to be up, and your net force is positive, then Fs goes down. If assuming that positive x is up, you obtain a negative number, then obviously the net force is bringing your object down, therefore Fs is up. Okay? And the advantage of this, let's calculate it. We'll see how useful this is going to be. F is, what, 30. Cosine alpha, alpha is 30. Cosine of 30 is square root of 3 over 2. Minus mg. M is 8. Roughly 80, if I take g to be 10. And then sine alpha. Sine alpha is sine of 30. Therefore, it should be 1/2. Which one is bigger? Roughly 40 or 15 times 1.7? 40. Therefore, this is negative. Therefore, the weight, the component of the weight along the inclined plane has much more effect and it cannot be sustained by F. Therefore, the whole system goes down. That's why it's negative, because I decided to choose positive up. Hence, my friction is up. Therefore, I know that my friction is right here. And that's Fs. But here's the beauty of this method. You know that you're using Newton's first law. Therefore, you know this is satisfied. This must be satisfied in the x direction. So now that you add Fs to it, obviously, for this to be equal, to change this to 0, as you add a F, which is positive, then obviously F would be the difference. Somebody just pressed the talk button and is not talking, and we have a background. Oh, thank you. Okay, so as you can see, as you do the test, the magnitude of your test will give you the magnitude of Fs automatically. It's a beauty. And since it is negative, and you assume it to be positive here, as you move it to the other side, Fs is positive. So Fs will be equal to 40 minus 15 times 1.7. So the problem is done. Okay? And then, of course, no more force. You get it by doing Newton in the y direction, where you're going to get N is equal to mg cosine alpha. In Newton again. Okay? So friction really assumes that we master Newton's method, because obviously, as you see, we're taking a shortcut left and right. That's the fail-safe method. You will never fail with this. If you decide that you don't want to do this, pick a direction. If you pick Fs up and then actually it was down, that's okay. As you solve for it, you're going to get a negative sign. You'll know exactly, oh, okay, wrong direction. Just mention it. Okay? So Fs is not easy unless you go step by step. And the key to Fs, remember, is the diagram. Whoops. Where's my diagram? Yeah. That's the key. That's the one that allows you to figure out the tendency of motion, which then allows you to figure out the direction of Fs, which is always opposite. So if you pick a positive x somewhere and you calculate this, if it's positive, then you know that your Fs is going in your negative x direction. But if after you pick a positive direction somewhere, you end up with a net force which is negative, then you know that the frictional force static is going in your positive x direction. So you will always have, with no ambiguity, the perfect direction of that force. Therefore, you will always be positive. So friction will take a lot of time to practice. So please, make sure you master all the NA and all the AS before you start tackling friction. If you start doing the F before mastering all the ones before, it's going to be very, very challenging. So you need to master everything that comes before. So let's see another example. What is 3? What is the difference? Isn't it the same problem? Huh, it's the same problem. Okay then. My bad. Seems like F2 and F3 are the same. Oh, question. Is there a unit of magnitude for which use for friction? The unit of magnitude. Are you asking what is the units of friction? Can anybody answer that question? What kind of concept is friction if it's something that shows up in a free body diagram? Excellent, Crystal. Yep, gotta be Newton. It's a force, right? The coefficient of static friction is unitless. No? Perfect, perfect. Here. It's right here. If you have blah blah times a force is equal to blah blah, let's do units analysis. The units of F is Newton. The units of normal force is Newton. Therefore, the units of US must be nothing. Hence, if we know the units of normal force is Newton, the units of F must be also Newton, so that this equal sign is true. So units analysis is very, very powerful. Always use it when can. If you're not sure what is the units of your analytical answer, just plug the units in there. And if it matches the units of what you're looking for, woohoo! This technique will allow you to know for sure if you're wrong. That is, if the units don't match, you know 100% that something is wrong. But if the units test do work, it does not tell you necessarily that your answer is right. So it only can allow you to figure out that your answer is wrong, not right. That is, if the units match, you still may have problems. Keep that in mind. It's only one way. All right. Well, let's look at F5 then. Okay, am I living in a crazy world, or they're all the same? Ah, no, they're not the same. Okay, I'm not living in a crazy world. NA5, they just have all the same diagram. Same situation. They're giving us the mass, they're giving us μs, μk, and alpha. But this time they're asking a different question. They're telling us to calculate the normal force and they're asking us to calculate the magnitude of F max such that the system is at equilibrium. All right. If the system is at equilibrium or maintain at equilibrium, they don't ask for the frictional force, but obviously we know it's there, so we have to consider it. If the system is if we're being told that the system is at equilibrium, maintain at equilibrium, are we dealing with static friction or kinetic friction? Yes, Jamie, absolutely. Absolutely. Excellent question. Keep that in mind as we're going to figure out its direction. Excellent, static. So we know it's Fs. Now the next question is, can we assume with 100% certainty that the static friction takes on its maximum value or not? How do you know that? What is the method for you to answer that question? What do you need to see for us to know and separate Fs from Fs max? No keyword. Are you sure? Read the problem carefully. There's only 3 keywords. You don't see any of those 3? Really? Wait, we're doing F5, huh? What? F5. I'm not the one taking a crazy pill. Am I? No, I'm not. Yeah. Remember what I said? Right here. You should have that on your notes. What did I say when we did the graph? Crap, where is it? Must have been before, so this one. I said specifically that those, obviously this keyword cannot be associated with Fs. This one may or may not. And this one is irrelevant. So those keywords don't have to be associated with F. Obviously minimum cannot be associated with Fs. Maximum may, but it could be associated with something else. Same as min, to an angle, or a weight, or I don't know, the maximum force of a tension. Doesn't matter, as long as they're here. Okay, so revise your note, update them. As long as you see any of those 3 keywords, doesn't matter to whom they apply, as long as you see them, you know Fs takes the maximum value. Okay? And again, min will never be associated with this frictional force, obviously. Max may, but it may be associated with something else, like in this case, 2 big F. But it could be associated with the angle. So what is the maximum angle that we could pick so that the system remains in equilibrium? That would be an example. Or what is the maximum of F such that the system starts to move? That would be another example. Good. So we know that maximum is identified in the problem. Therefore, we know we're dealing with Fs max. Therefore, we know we can use its functional form, μSn. All right. If we're equilibrium, which law are we going to be able to use? Newton's first, second, or third? First, excellent. So let's apply Newton's first law. Now that we know for sure, we can use Fs max and we can use center force is equal to 0. We're looking for 2 dudes and an F max. We know as we apply Newton's first law to that system, it's a 2D problem, therefore we're going to pick up 2 equations. Life should be easy. Let's complete a free body diagram. We can sketch it here. We have the weight, we have the force, we have the normal force, and we have Fs again. We're going to be facing the same situation. The only possible direction of motion is along the inclined plane. It could be up or it could be down. F can be redrawn here. Okay? So if the weight, the component of the weight along X is bigger than the component of F along the inclined plane, then the tendency is up, friction is down. I'm sorry, what did I say? If the component of the weight along the inclined plane is bigger than the component of F along the inclined plane, then the tendency is to go down, Fs max is up, and vice versa. So, the great thing about Fs max is, if you know you can use Fs max, and you're at the state where you're trying to figure out the direction, there is another method to figure it out with foolproof. And the method is, if the keyword max is associated to a force or a direction, take the limit for which it's a huge number, because obviously it's max. So Jamie, I'm going to address your question earlier. If F takes its maximum value, and that's what we're trying to figure out, well, obviously this will be bigger than that. So whenever you see the keyword max and it's associated with a force, you know for sure that the tendency of motion is aligned with this quantity. So imagine it's huge. Therefore, this component must be huge, and it will always win with respect to the other. Therefore, the tendency of motion is up. Therefore, right away, Fs max is down. Similarly, if the question was different, and the question was asking you, what is the minimum force F that I can apply for the system to remain in equilibrium? Then obviously, the tendency of the object is to go down. So whenever you see the keyword min, to try to figure out the direction, imagine it's not there, and look at the tendency of motion. So as I repeat again, Jamie, in summary, whenever you see the max keyword, always imagine that the quantity to which max is related to is huge. Therefore, the tendency of motion will be the same as the tendency of what you're looking for, that is associated with max. If you are dealing with the keyword min, then imagine that it's not there, and look at the tendency of motion without it. For example, if you're looking for F min, and F is here, imagine F is not here. The only one that remains is this one. Therefore, of course, the tendency is to go down. Therefore, USN will be up. Exactly. Okay? So just by looking at the keyword and ask yourself another question for each, you will figure out the direction of that stupid force. All right? That's it. Now we can complete the problem. We've done this before. Obviously, this is alpha. Obviously, this is alpha. We're figuring out F, max, and N. So, obviously, we'll have same equation as before. F cosine alpha minus mg sine alpha minus USN. And this is equal to 0. And in the y, we'll have N minus F sine minus mg cosine. And this F is F max. Two equations to unknown. Okay? 1 and 2. Easy. Again, please redo this problem and look for F min. As you go through the process of completing a field diagram, you see the keyword min. It's associated with big F. Therefore, imagine that it's not there. Take it out. Then you realize the only two forces present are N and W. Which one is going to cause any motion along the inclined plane? Can only be W. And you know, because you mastered chapter 2, the component of W is obviously down. Same as before. Thank you for pointing that out. So obviously, if you take out big F, if you're looking for F min, the only component that remains along the possible direction of motion, which you can call X if you want, or Y, or whatever, is obviously this one. Therefore, the tendency of motion is to go down. Therefore, mu Sn is going to be up. Which means that this sign is going to change. And as you change this sign to a positive, then this F is going to become minimum, and this one minimum. So please, redo this. It's a very, very important problem. Very simple, but very important to help us identifying the direction of that stupid static friction if it ends up being maximum. In all the other cases, we won't be able to do that if we don't see those keywords. USN came from because we've all agreed that this was approved. Correct? So I just wrote this functional form directly like I do with W. Sometimes I put mg, something. Instead of call it Fs max, I put this functional form and I've just put USN directly. Because we did that step already. So we know Fs max or Fs is max, therefore E is equal to USN. Perfect. Okay? So static friction is and can be very, very tricky. So make sure that you do study it. Yep, along the x-axis, yeah. So in this case it will be negative. Let's do a problem with Fk. And you will see that Fk is much, much easier. Let's do an easy one. Let's do F6. So, same output system. Again, we won't have time to redo all the output system, all the types with friction. Make sure you do them. Type 2, type 3, type 4. Redo all those output system with friction. So 2 are given to us in 6 and 7, type 2. Make sure you reproduce this in type 3 and type 4. Type 2. They're giving us all the masses as usual. MA, MB, mu S, mu K, and they're asking us for the same question, acceleration. Same as before. So the only new thing is friction. Obviously, object A has no ambiguity in its direction of motion, it's down, and B is right. So we're going to do the exact same thing as before. The only difference is we're going to have a new force on B. Right? So let's duplicate what we had before. MAG, T, T, N, MBG, and obviously if B is moving, is being accelerated towards the right, and guarantee we know we're dealing with FK. Therefore, this is mu Kn. Much easier, right? As long as you identify the direction of motion, FK is easy. So really the equation is exactly the same as before. The only difference is you're going to get MAG minus T is equal to MAA. That's for object A. And for object B, you're going to have the same two equations, except before we only had T is equal to MBA. Now we have T minus the friction. So the acceleration is going to be a little less because of that stupid term. And then the last one is N minus MBG is equal to 0. So now we cannot solve this problem with only two equations because we have three unknown due to the friction, A, T, and N. So we need that third one. So we're dealing with a 3 by 3, no biggie. As you solve for A, we can substitute N after we solve for it here, and then we can add those two equations again, and you will end up with MAG, this will disappear, minus mu K MBG is equal to MAA plus MAB, or MBA, sorry. Hence, as you solve for A, before we had MA divided by MA plus MB times G when we had no friction. The only new thing here is we have a new term, which of course, since it's negative, will slow down the acceleration, as expected. So really the new thing is just this guy. And again, the sign matches the physical constraint. MA is going to contribute to the positive acceleration down for A, right for B, and MB, associated with the mu K, is going to tend to slow down the system. Therefore, it has to have the negative sign. Okay? Questions on friction? I do understand, I'm guessing that it is a lot. The method has way more steps now that we have added friction. Make sure you write your notes, make sure that it makes sense to you, and make sure that you use it. As you use the method that we have updated with friction, we have added a bunch of questions. If you don't skip them, sure, lots of steps, but you will always get it right. Every time I see people ignoring the method or skipping steps, I know the answer is wrong, guaranteed. And that's what happened in the first test. Even for the non-WI, if I can see a coordinate system or simplified equation, statistically those people did good. But when I didn't see anything, I just look for the answer, guaranteed, they're all wrong. And that's what happened on the first test. So if you like to improve your grade, if you didn't get what you expected, make sure you go back and review, and from now on, follow the method that we go over and spend so much time on. It will make a huge difference. Yes, exactly, Jamie. Nope. F only have 3 atwood, right? F6, F7, F9. 6 and 7 are type 2. F9 is type... Oh, it's another type 5. So you want to go back to, say, AS3 and the one we call AS4, and then add friction in there. And then you can handle F9. But we'll do F9 together again on Wednesday as we finalize this chapter. We just have to go over rotational motion, drag, and we're good to go. Or unlisted, won't we need? Yes, Jamie. Make up your own problems. Use the same settings as would. Just add friction. Pick numbers. Who cares? Okay, so you say go back to AS3, and then you're going to decide, okay, I'm going to redo AS3, but now there's going to be friction between object A and the inclined plane. And then you're going to decide, okay, whatever, US is 0.2, UK 0.1. Are you supposed to know? You work it out. You take a picture with your phone and send it to me via attachment. As I ask so many times for you to do so. Or you stop by my office. Okay? Yeah, pick numbers, take a picture, let me know. Or look at your book. I'm sure there's many within your book that involves friction. So work with those first. Okay? AS3, AS4. Yeah, just make them up. Make them up. Cool. Questions on this? So on Wednesday, I will assume that you've done all those problems, you mastered them with friction. We're going to revisit any problems that you may want to revisit as you are redoing them, so that if you got stuck somewhere, we'll fix it up. Then we'll do F9 together, and then we'll introduce circular motion, and then we're done. And as an application to circular motion, we're going to use the bank curve, which is already worked out on the homework page. So make sure you look at HWKC bank curve, without and with friction. So we can go fast on this since everything is laid out with the solution and the video. And then we mentioned drag, and then we can move on to energy and work, which is going to be chapter 2, 3, 4, 5, 6, 7, and 8. And then we can have the second test. Okay? Alright. Let's take a quick break. If you would like to stay WI and have some issue with your LaTeX for the next problem that you just received today, feel free to stay. If everything is good and you don't need to talk about anything that's WI related, feel free to go. And regardless whether you're in WI or non-WI, if you like to stay for office hours and revisit any of the stuff we did today, or stuff that we haven't covered but you have already covered, please stay and we'll work them out.